Let's check for the problem of autocorrelation in our dataset. Let's look at one of the classical linear regression model assumption, which is autocorrelation. And we are going to look at how to detect autocorrelation in your model, when this assumption is violated, and what is the effect if this assumption is violated in your model, and how do you correct for the problem of autocorrelation in our model. First and foremost, the assumption of autocorrelation. Now, it could be used interdependently with autocorrelation and serial correlation, depending on the type of analysis you are performing at hand. You might be performing analysis of a time series dataset or the cross-sectional dataset. So that's why you can either be talking about autocorrelation or serial correlation, especially when you are dealing with the time series dataset. You'll be talking about serial correlation. So now, what is this assumption of autocorrelation? Just like the multicollinearity that says that independent variables of your model should not influence each other. There should be no there should be no exact relationship among the independent variable of your model. That of autocorrelation deals with the random error time or the disturbance error time. That is, there is no relationship, there should be no correlation between the random error time of your model. The random error time should not influence each other in your model or in your dataset. Once there's a violation of this assumption, then there will be that will lead to a problem in your estimate in your model. That means your model your estimate of your model will actually result in wrong policy formation or a wrong decision making. So now, what is the effect of the violation of this assumption of no autocollinearity in our dataset? Okay, now once there is this violation of this assumption, now your estimate is similar to autocorrelation, is similar to the problem of heteroscedasticity. Your estimate from the model is still linear and is still unbiased. But the problem is that it's no longer best. In other words, the estimate that is produced by your model does not meet the criteria of the minimum variance. That is, there is a deviation between the expected value and the estimated value and the true value of your dataset. So there is a big gap, a wide deviation between the estimated and the mean value and the true value of the dataset. So now, there's still your model, your estimate they are still linear, they're still unbiased, but they are no longer best. That means it has no minimum variance. And secondly, the estimate of the true variance is biased. Now your estimate for the true variance is what? Biased. So now that is that once the first assumption is violated, your estimate is still linear, is still unbiased, but is no longer with minimum variance, and the variance is biased. The biasness of the variance is not known. It will lead to influence or increase the value of your estimate. Now the variance of it increases the value of the variance of your estimate. Now, once it increases the value of the variance of your estimate, that will affect your hypothesis testing. It will make you to accept a false null hypothesis when you should reject it, and to reject a true null hypothesis when you should accept it. So that leads us to the third effect of violation of the assumption of no autocollinearity in a model. That it will affect the T and the F test. The T and F test become what? Biased. The T test is used to test the individual influence of the variable on the dependent variable, while the F test talks about the overall influence of the dependent variable on the dependent variable. Now, how do we correct for this? Now, one way to correct for this, we use the heteroscedasticity autocorrelation consistency standard error method. That could be used to correct it, or we can use the weighted least square method. Now, we can use the weighted least square method just like the heteroscedasticity method, which we could talk about the generalized linear model. Okay, that's generalized. Also, we could talk about this with the model specification. In other words, the problem of the violation of this assumption of no autocorrelation in your dataset might be as a result of wrong model specification. So you have to check your model specification if it is in order. Then now, in order to detect if there is autocorrelation in your dataset or your dataset, in order to diagnose if your dataset has the problem of autocorrelation in it, or there is a problem of autocorrelation in your dataset. Now, to diagnose this, we have to install these packages. We have to install the performance package and the LM test package. I've always installed these two packages. So even the performance package already have that. So you run this line of code. The moment you run this line of code, that helps you to install that particular package and to activate it as well. So this helps to install the NM test package. Helps to install the NMX test package. So now you can see the first one I make use of a double quote, and the second one is no double quote. So you run those two lines of code. Now I want to import my dataset. My dataset is located in R, and my dataset is located in an Excel spreadsheet. You can see the extension XLXSX. So I'm going to import that dataset into R. So I'm going to run this line of code, but I'm going to call this auto. Now I'm going to use this function to import it into my R program because my dataset is located in an Excel spreadsheet, or I can use read Excel to import the dataset into my Excel spreadsheet. So you can use either of them to import the dataset into your Excel spreadsheet. Now I've used that. You can see that it has already been imported into my Excel spreadsheet. So that is my dataset. Now you can see that this is my dataset. And my dataset deals with the sales of cars, and I'm interested to see if the sales of cars is influenced by the type of vehicle, and if the sales of car is influenced by the engine size, as well if the sales of car is influenced by the fuel capacity represented by the MPG variable. So you could either run that line of code or you run this line of code. Both are similar because my dataset is located in R. So I can use this function or the previous one. Now I've run that, and now you can see that my dataset, I have a lot of columns. I'm only interested in selected columns. So I'm going to select the columns that I'm interested in. So I'm going to give that a name. I'll call that car auto. And I'm going to introduce a pipe function. Now I'm going to introduce the pipe function. Then I use the select function to select this. Now the moment I do that, that selects it, and this I'm going to save this in an object known as car sales auto. So I'm going to save in an object known as car sales auto. I'm going to run this line of code as well again. That saves it in a car sales auto. Then I'm going to run this particular line of code. I'm going to run this regression. Now, this is my dataset. I've changed the name of my dataset to this car sales auto. So I'm going to run this line of code. That runs that for me. I'm going to run this other line of code. Now that brings out the coefficients. Now you can see the coefficients, and if I want to see the t statistics, the standard error, and the p-value, I'm going to use the summaries. Now it gives me that. Now you can see only the types of vehicle have influence on the sales of vehicle, while the engine size and the fuel efficiency does not affect the sales of vehicle. You can see the p-value, the standard error, and the rest of that. Yeah, okay, fine. Now we've done that, we want to check if this model has the problem of autocorrelation. First of all, we could check a model assumption. We could just use this check model function. So we can use this check model function and we introduce the RM here and quickly run this line of code. Now I'm going to run that line of code. Now you can see that. Now let's draw this up a bit. Now the space is still small for that. Okay, fine. Now you can see that. Now you can see for the autocorrelation problem, we have this from normality. For the problem of normality, that's what's about the random error of the 10 should be normally distributed, and influencer observer point should be inside the autocorrelation. Then we look the model predicted line should resemble the observed dataset. And this is almost this collinearity problem, normality problem, almost identity problem, and okay, let's see. Let's use let's make use of the LM test. Let's use some of the LM test. Let's see. We have the Godfrey test of higher order serial correlation. We can use this test to test for presence of autocorrelation in a dataset. We can see test for serial correlation for up order up to 1. We could see that the p-value is 0 point something. Now this will tell you that we accept the null hypothesis of no autocorrelation in a model. Now that means since the p-value is 0, that means we reject the null hypothesis of no autocorrelation in a dataset. In other words, there is autocorrelation in a dataset. Let's try another test. There are other tests that can be used. The LM test. Okay, there are other tests we can use. Now we have the double waxing test. Okay, the double waxing statistic test can also help to detect for the problem of autocorrelation in a dataset. Now, alternative hypothesis, true autocorrelation is greater than 0. Now you can see the p-value will reject the null hypothesis of no autocorrelation in a model, that a model is not suffering from the problem of autocorrelation. Now, based on this diagnostic statistics, we can see that the null hypothesis is rejected. The null hypothesis of no autocorrelation in a model specification is being rejected. That we accept the alternative hypothesis because yes, a true autocorrelation is greater than 1. Now we can see the p-value for this, and we can see the p-value for this other test. Now, these are the double waxing statistics test and the proof. Here is the proof Godfrey test. Now we've seen that there is the problem of autocorrelation in our dataset. How do we correct for this problem of autocorrelation in our dataset? Just like the problem of heteroscedasticity, we can also use this by transforming our dataset. So what we need to do is to come just to transform our data set, we have also correlation here is equal to this. This way, we introduce the pipe function and we use the mutate function. Now, using this mutate function will help us to. Let me just quickly use this. But I thought we could just simply rerun this model by just changing this to the log of this. That's how to correct for the problem of autocorrelation. Just run the log of that. That's one of the ways to correct for the problem of autocorrelation by transforming your dataset, by transforming your model using the logarithm specification for your dataset. You use it to run your model, and that will help in correcting the problem of autocorrelation. Now I can use this now. First, we can see the p-value is still 0.0. That means there's still problem of autocorrelation in this data. So because we reject the null hypothesis of no autocorrelation, now you can see that the hypothesis true autocorrelation is greater than 1. Now I've introduced the log-linear model. I mean, I've changed my model specification because one of the methods of correcting for autocorrelation is to change your model specification. Now, you could decide to now introduce log to all your data sets if that does not solve the problem. And you keep on doing one and different methods to see until the problem is being rectified. So what I wanted to do here is this. I didn't want to affect this model. Instead of using this, I wanted to do the mutate function here. Okay, I just wanted to do the mutate function, and I pick this and I say, okay, now let the L sales to be equal to sales is equal to type. Then the engine size equals to the engine size, and then we have this. Okay, now I've done that. So what am I going to do now? I'm now going to copy this. I'm going to save this in an object known as okay, now this function to we run this. Then when we run this line of code, if everything is done correctly, then I'll just grab this. I bring it down here, and I just simply where's the L sales equals to sales. So what I have here will just be the L sales, regress it on this. And now my data as the name of my data has just changed. So I call that. So if everything is done properly, we run this particular line of code and then it gives us a nice result. It gives us an output. Now, so I run that particular line of code and then Now you can see, so we can see that this, so we can do that. So one of the way of correcting for the problem of autocorrelation, the ways of correcting, not one of the ways of correcting for problem of autocorrelation is your model specification. Just as I've introduced the log linear model. First and foremost, I only use the linear model, but now I'm using the log linear model. But they still detected the problem of autocorrelation. You can still go ahead and use the log model in your dataset, and you keep on doing one or two things, or you can rather use the weighted least square, or that is a generalized least square, to run your regression model, and that will help to correct the problem of autocorrelation. If you like this video, don't forget to give it a thumb up. Don't forget to subscribe to our social media channel, our Instagram channel, our TikTok and Facebook channel. And don't forget to share our video. Give us a thumb up, and see you in the next video.